Okay, so if I was forming an ion, or I should say, if barium was forming an ion, so we have Ba, what would be the charge on barium?
Two.
Okay, so we have barium would be 2 plus. Okay, and let's say we had bromine. What would be the charge on bromine?
-2.
-1.
-1. So why isn't it -2?
Because then
Good job, Xavier. Because of what? Are you there? I think you cut out. Anybody want to fill in what she was saying? Because I think it dropped. The signal dropped. At least I didn't hear it. So why is bromine a -1 and not a -2?
Because it only needs one electron to be a noble gas.
Because it only needs one electron to be a noble gas. That's right. Good job, Xavier. He's quick on that typing, haven't he? Okay, so now if these guys are going to get together, how many bromines are we going to need to balance out the barium? 2 plus. Because when we form ionic compounds, that ionic compound has a total charge of 0. So how many bromines am I going to need to balance out the barium? 2 plus.
2.
2. So when these guys come together, the way that we would write it is Ba, Br, 2 with the subscript. Okay, you'll notice no charges, right? Because they're neutral now because they're together. Okay, piece of cake. So how many of you guys have done homework number 4 or started number 4?
I finished
Yeah.
it.
You finished it?
Yeah.
You go, girl. Okay, so at the very end, right? That's what this was, right? If I remember correctly.
Yeah.
Okay. So if I have a, it's called a polyatomic ion. So NO2 minus, right? So this guy is considered a polyatomic ion. So this whole thing, NO2, has a minus charge associated with it. Okay, it's called a polyatomic ion because it's made of multiple atoms, poly meaning many atoms. So there's an N and an O. Okay, so if I have this polyatomic ion, and let's say we're interacting with this metal that has a 3 plus. Okay, so how many of these, this guy's called, it's called nitrite. How many of these nitrite ions will I need to balance out this?
Would it be 3?
How many?
Would it be 3?
I would need 3. So the way I would write this is, because this guy is represented by the whole all together, right? That ion is all together. I'm going to have to use a parentheses. So I would write that as the parentheses NO2, and I have 3 of them. Okay, so the parentheses tells me that everything that's inside of there, there are going to be 3 of those. You guys see that?
Yeah.
So let me give you a challenging one. What about this guy?
Two of them.
I'll need two of which one?
The PO4. 3.
Okay, so that gives me a total charge of what? If I have two of these, that'll be -6. So you're telling me that I have one of these?
No, you need 3 of those.
I need 3 of those. Okay, so I'll answer your question in a second, Diana. I'm not dismissing you entirely. So in this case, I'd write, since there's only this ion, it's just that Mg, it's not a polyatomic ion, we're just going to write Mg 3 parentheses PO4 2, okay? Do you guys get that?
Yeah.
Okay, Diana, the ionic charge, these numbers here, either they're given to you because they're a polyatomic ion and they have that charge, they're known to have that charge, or you have to calculate them based upon the ion that they would form. So where's magnesium, Diana? Circle it on my screen. You remember how to do that? Okay, thank you, Naomi. Okay, so we have magnesium, right? And if magnesium, like all elements on the periodic table, want to be like who, Diana? Who are the cool kids, Diana? Anybody want to help her out?
Noble gases.
The noble gases. Can you show me where the noble gases are at? Anyone?
Oh, it's the purple column on the right side.
Which group would that be?
Helium, neon, argon.
You can give me the number. You can say group 18, right? Good job, Diana. Yeah. Okay, so the ones that were circled on the right side are the noble gases. Now, what does magnesium need to do to be like a noble gas? It has two options. One option, it can go and add 1, 2, 3, 4, 5, 6 electrons. Or it can go and lose 2 electrons. 1, 2, and then it's like neon. Now, Diana, if you had to mow 6 lawns, or if you had to mow 2 lawns for the same amount of money, we'll say $500, right? Would you mow 2 lawns or would you mow 6 lawns?
2.
Okay. Now, that's exactly what's going to happen with magnesium. It's going to go the easiest way. It's going to go 2. It's a lot easier for it. But then if you lose 2 electrons, then you're going to have what charge? Because electrons are negatively charged. So that ion is going to have what charge now? If it starts off at 0.
Be positive.
So it's going to be a 2+. So that's where you get your 2+ from.
So
Okay.
when you're counting to the right, it would be adding electrons. Like if you're counting right to get to the noble gas, it'd be adding electrons.
So if I was going this way, this would be adding electrons, yes. If
Okay,
I'm going the other way, I'm losing electrons.
gotcha.
Okay.
How'd you
And
get
you always want to go the easiest and quickest route, right?
Yeah.
how'd you get the 2 on front of the PO? Because since it's 2 of them, that's what it's.
Because what is the charge on the PO who asked that question? Whoever asked the question, it doesn't matter. What is the charge on it? What did I tell you the charge was? What's written up here?
3 negative.
3 negative. Okay, so that means it has a -3 charge. Okay,
Uh-huh.
so if it has a -3 charge and I want it to balance out with magnesium, which has what charge does it have?
2 positive.
2 positive. So if I have 2 minus 3, does that equal 0?
No.
It doesn't. So how can I make 2 minus 3 equals 0?
You do a positive 2.
Uh-huh. So if I multiply, let's say I multiply the first one by, so 3 times 2 is what?
6.
6. Okay, so that equals 6. And then if I have 2 times -3, what does that equal?
-6.
Okay, and if I add those two together, what does that equal?
0.
Okay, and that's my goal, right? By them coming together, because ultimately you want to try to balance out your ionic compound. That's a lower energy state than just being charged alone. So, okay,
Okay. Thank you.
so it's just simple math. You want to try one more and then we'll move on?
Yeah.
Let's do. So if I have Al and O, so what is going to be the ion formed, and then how would I balance it out?
Do we have to find the charges first, right?
Yep.
Gonna
So
be
it'd be
3 plus for the aluminum.
Okay. So it'll be Al 3 plus. Good job, Marie. And then what about?
then
Negative.
2 minus negative.
So that was a team effort. I couldn't pick out who said it at first, but good job. Okay, so now we got the charges. So then what are we going to do?
balance them out.
Okay, so how do we balance them out? How many of these guys will we need and how many of these guys will we need?
Three.
3 of what? Do I need 3 of both of them?
No.
2 aluminum.
3, you said 3 aluminum?
2.
2.
2 aluminum. 2 aluminum
3 oxygen.
And 3
and 3 oxygen. Okay, so then my chemical formula is going to be
Al2O3.
correct?
So you're kind of basically just flipping around the little numbers, right?
Yes, cross multiplying what a lot of people would say. So you take this number, you multiply it by that, but you just use the number, not the
Not the
sign,
sign.
not a plus or minus. Yeah, and then the same thing with that one. Yeah. Piece of cake.
Yeah.
Sort of.
All it is simple math, right? Nothing too complicated. It's not like doing derivatives or, okay?
How you write the chemical formula of an ionic compound?
This is how you write the chemical formula for an ionic compound, yes. Okay? Okay, good. Let's see. We talked about conductivity of ionic compounds.
I don't think so.
You don't think so? God, I have a slide. Okay, so we're going to do this. This is what we're going to do. Then we'll just work our way through. Okay, so you guys. Okay, so you guys know what ionic bonds are. You're very familiar. So two ions coming together, they're going to have to neutralize each other. Because they're going to be neutralizing each other, they're going to form what we call a crystal lattice. And I'll show you what a crystal lattice looks like. Ultimately, at the end of the day, you're going to have balanced charges. It's going to equal 0. You notice, did you guys notice something? All of those compounds we wrote Al2O3. You never ever saw Al3 plus 2 down here, O3, 2 minus. You never saw that, right?
No.
You never want to write it like this. That is wrong, okay? Because they're neutral now. When they come together, they're neutral. So you don't want to have those charges showing, okay?
Okay.
So it's always written like this. If you have charges, that means it's an ion, right? That means they haven't been neutralized, okay? Okay, so a couple of things that we want to know about ionic compound. Those bonds, that interaction, that plus and minus, that's a strong thing, right? So there's only a couple of things that are going to kind of separate them. One of those things is a lot of heat. So you have to make it a liquid, right? A severe liquid to get those bonds to kind of loosen up. And if it's a severe liquid, then that means you're exposing those plus or minus charges. Now, when you're exposing those plus or minus charges, you're able to conduct electricity because the plus is available for that minus to interact. Because we know that electrons, what are electrons? I mean, what is electricity? Sorry, not electron. What is electricity? Anyone? Electricity. Let me spell it for you.
Electrons?
So electricity is just the movement of electrons. So electrons are basically being moved through the wires, right? And they're being moved through the wires because you're getting the metal, right? It becomes plus because it's going to delocalize an electron. And then it interacts with that electron. And then that interacts with the next electron. And then, so it gets carried along. Like, have you guys set up dominoes, right? And tilted them over,
Yeah.
right?
Yeah.
It's like that, right? So you're going plus, minus. So you're just shifting, right? And you're shifting that electron along the way. So that's what a wire does. So you can do this in solution if you have plus and minuses being exposed, right? But if it's together, if it's a solid, right? Like salt, you never see anybody hooking up a battery to salt, right? Have you ever seen that?
No.
And you won't, because it won't conduct electricity, right? If it's a liquid, if we melt the salt, it'll be able to conduct electricity. And I'll show you that here in a second, okay? So ionic compounds, if they're dissolved in an aqueous solution, like, do you guys know how you dissolve water? I mean, dissolve salt in water?
Yeah.
Okay, so kind of like we dissolve salt in water, it exposes the ions. So what happens is we break up that happy marriage between sodium and chlorine. Now water is a polar covalent bond. We've talked about that already, right? So this guy is going to be partially positive. This guy is going to be partially negative. Now, what I mean by partially positive and partially negative, meaning that they don't have a complete charge like sodium and chlorine, right? They're only partially because they're sharing the electrons. The electrons are going to be spending more time around the oxygen than it is going to be spending around the hydrogen, right? So the electrons form what we call a dipole moment. Okay? Electrons, this shows us where the electron is going to be spending more time at. So, like if me and my wife got a divorce and we had kids, right? So the kid would spend the majority of the time with me and only a little time with my wife because I'm the better parent, right? Okay?
Yeah.
So it's along those same lines, right? We're sharing the kid, right? But I'm the better parent, so it's going to spend more time. Okay. Now,
Doubt it.
are you hating on me? What are you saying?
Sure am.
Haters, haterade. Okay. Okay. So in that context, we have that partially positive and that partially negative forming, right? So that positive is going to be interacting. Let's pick this up. That partially positive is going to be interacting with that negative ion, and that partially negative is going to be interacting with that positive ion, right? Because those opposites, right? Positive. Okay. So then all of your oxygens are going to orient towards the sodium, and all of your hydrogens are going to orient towards your chlorine, and they're just going to surround them. And that's what keeps them in solution. But it keeps them so they're exposing their ionic charge. So then we're able to conduct electricity through salt water, right? Where if we just had water alone, these charges are not strong enough to conduct electricity. Okay, so water alone doesn't conduct electricity, but salt water does. Okay. So this is just basically showing us if we had sodium metal with chlorine gas. So sodium metal is so anxious to get rid of its electron that it's like, oh, finally I have a reason to get rid of my electron. Here, you have it, you have it. And chlorine is so anxious to take it, so they form a very violent reaction because of that, because they're both so anxious to sit there and do it. They're anxious to react because they want to be like a noble gas. And this gives them that opportunity. So all you're doing is transferring that electron from sodium to chlorine. So chlorine forms the chloride ion. And then the sodium becomes positive and it forms the sodium ion. Okay? And so now you have that honest to goodness plus and that minus. And they take advantage of that. Now opposites attract. They're going to come together. They're going to form what we call a crystal lattice. And that's what's shown here. So this is a salt crystal. This is what it looks like on the molecular level. Okay, so this is just another detailed showing you where the sodium is the black and then the green is the chlorine ion or chloride ion. So the sodium ion, the chloride ion. And so they're alternating and they're interacting as kind of as a group. You know, so you have sodium alternating with chlorine, alternating with sodium, alternating with chlorine. And so you get this beautiful lattice pack structure, right? Okay. So this is showing you when we melt salt. Now you need a lot of energy to melt salt. So we could actually do it with the Bunsen burner. It'll take a while and it has to get really, really hot. Now we have this connected to a battery. If we didn't have salt, if we just put it straight in the salt, we wouldn't get no signal at all. But the fact that we get a signal means that these electrons, or I should say, that ionic compound is being dissociated a little bit. So we're able to get some exposure to that plus and minus values. Okay, by us putting a lot of energy in it, we're separating that interaction between the sodium ion and the chlorine ion. Okay, and then that allows electricity to be able to flow through. Simple. Veronique. I know I butchered it. Since you're criticizing me about my parroting here,
Yeah, what's
is
going
it
on?
simple? What was that?
I said, yeah, what's going on?
Is it simple? Do you see it? Can you understand it?
It's not simple for me at all. It's actually super confusing, but I'm trying
Okay.
to figure it out.
Okay. That's good. That's all I can ask.
Yeah. I mean, I'm
So-
not on top of it at all, but we're trying.
So bottom line is that we have the sodium chloride. When it's a salt, it's together. But when we start heating up, we start disrupting that ionic bond. So then you're starting getting some of these guys, just the ions alone in solution. When it's a liquid, you're getting a lot of these available. So that means if I have an electron that comes along, this electron is able to interact with this guy. And so then this guy becomes like it's neutral, right? So, but then this guy has a negative charge. So then it carries on that negative charge, and then that interacts with the next sodium. And then you're just getting a carry on with charges, right? And so
Okay.
and that allows the electricity to flow. That
All right.
electron is being carried on using the charges of that chloride. Okay.
All right. That's a little bit easier to follow.
Okay, so we've talked about covalent bonds. You guys, have we drawn those dot structures? We haven't drawn those dot structures. That's what you're telling me, right?
No.
So covalent bonds are electrons that are being shared, right? So if we're sharing electrons, that means we're not giving up electrons. So like sodium chloride, we're giving up an electron, right? Here we're actually sharing electrons. So, and there are going to be two ways to share an electron. I'm going to talk to you about both ways. I like to give you guys analogies. Did I talk to you about how I share stuff with my sisters?
Yes.
I did.
You
So we
talked
did
about
talk
how
about
you shared a toy with your
A
brother.
video game?
the
Christmas.
video game. Yes. So we did talk about covalent and non-covalent.
We
right?
did talk about covalent bonds, yes.
Okay. So, but I believe that I drew up some figures, some chemicals that we wanted to do bonds with. I'm gonna have to look at my notes, watch my videos. I didn't put CO2 up there and CO. Or noble gases into. Okay, it don't matter. We're gonna go over it anyway. We're gonna have to go back. I know I did. I may be getting old, but I'm pretty sure I did. This is what happens when you have like 6 classes that are teaching exactly the same thing. I'm like, I know I taught this. Okay. Triple bond. Yeah. Okay, good. Okay, so let's talk about the Lewis dots, right? So we know that hydrogen has how many valence electrons?
1.
It has 1 valence electron. Hydrogen is a special case. It wants to be like helium. Helium has how many electrons total? It has 2, right? So it wants to be like the noble gas helium. So hydrogen only needs to have 2 electrons to be like the noble gas it wants to be like. So in this case, you have this hydrogen and this hydrogen. They're going to come together and form a bond. The way that we draw a bond, the sharing of 2 electrons, we draw it with a line, okay? We put those 2 electrons between those 2 molecules or the 2 atoms, and then that means that they're sharing. And then we just draw that line there, okay? So this forms what we call a single bond. So if we have O2, which is a diatomic, what are your diatomics? Can you remind me?
Have no fear of ice cold beer.
Have no fear of ice cold beer. So that means
Hydrogen,
Nitrogen.
nitrogen,
Nitrogen.
chlorine, oxygen, iodine, chlorine, and bromine. Bromine.
oops. You guys are so fast. Okay. Okay, so let's go ahead. We're going to do this one, and we're going to do this one. So if we have oxygen, how many valence electrons does oxygen have?
6.
6. And how did you calculate the number of the valence electrons?
They're in that group.
They're in that group. Is there a way that I can look on the periodic table and figure that out?
Counted to the left.
Counted, yeah.
Count it to the left. Okay, so in that same row,
No, to the right.
or to the, okay, wait a minute. Hold on. I got to the right, to the left. I feel like I'm doing a dance here. Now dip, baby.
Well, you can either count to the right from starting from the group 1 to the right to where the element you want, or you can count backwards.
Okay, so I can go, if I started here, I can go 1, 2, 3, 4, 5, 6. Or I could say, I know that all noble gases have 8 around them except for helium.
Yeah.
So then I can go 9, I'm sorry, it would be 8,
7.
7, 6.
Okay.
So I start at 8, 7, 6. So that would be one way of doing it, or I can go 1, 2, 3, 4, 5, 6. Okay.
And all those in that group will have 6 valence.
Yep.
Right.
All of these guys will have 6 valence. And then all of these guys will have how many valence?
5.
5.
And these guys would have how many valence?
4.
And these guys,
3.
these guys.
2. And 1.
Does that rule apply for the ones way at the bottom?
Down here. So all of the ones in this row, yes. All the ones in this row, yes. All the ones that are in this row, yes, 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 yes. Although these guys are called post-transitional metals, right? They're going to behave crazy every once in a while. Your metalloids, for the most part, are going to obey that rule, but there are going to be some exceptions that are going to act kind of crazy, okay? And then these guys are transitional metals. That rule does not apply. Transitional metals are constantly changing. That's why we call them transition metals, okay?
I think she was talking about the bottom 2 lines.
Oh, you're talking about down here?
Yeah, the
Oh.
way bottom ones.
These don't apply either. They're considered like your transitional metals as well too. They're a hot mess. They're very complicated.
Okay.
And they can have definitely a lot of different changes. So, and we'll talk about that though. I promise. Okay, so we're talking about oxygens, right? So we have 6 valence electrons. Can you guys see my 6 valence electrons?
Yes.
Purple. Okay, so what I want to do is figure out a way so that they're like the noble gases, so they have 8 electrons around them. So let's move some of these electrons around. So if
2
I
bonds?
remove, yeah, to try to form bonds, yes. So they're going to be sharing electrons so that they can be like a noble gas.
Oh, yeah, it's like a noble gas.
Okay, so if I do that, move these 2 to the middle.
A single bond?
I'm taking 2 here and 2 from here. So
Oh,
is
double bond, yeah.
that'll be a double bond. Okay, now remember that line represents 2 electrons. So count the number that are around this oxygen.
8.
Okay, and what about this oxygen?
8 as well.
Okay, is that like the noble gases who have 8 around them all the time?
Yes.
Yeah.
Okay, so we're good. Now, what about, let's do F2. How many valence electrons does F2 have? I mean, that F has.
7.
Okay. 1, 2, 3, 4, 5, 6, 7. Oops. So we have a total of 14 electrons to work with, right? Okay. So how many will this need to share for it to reach its octet?
1.
Okay, so we're going to share 1 from each one. So count the number of electrons around fluorine from each of the fluorines.
8 and 8.
Yeah.
Okay, so are we happy? Is it cool?
Yes.
Mhm.
Yes.
Now, since these guys are exactly the same atoms, they're going to have the same pull, the same electronegativity, right? So these guys are going to be sharing evenly. Okay? So let's do one more and then we'll move on. Okay? N2.
5.
So 10 bonds or 10 electrons.
So we have 10 valence electrons, 5 around each one. Okay? So how many electrons have to be shared for them to reach their octet? Meaning having 8 around them, octet.
Is it 1 each? Oh, no, sorry, I counted wrong.
3.
Yeah, 3.
3 bonds? 3 bonds or 3 electrons?
3 electrons.
3 electrons each.
Okay, so each one has to have 3 electrons to share. So then that's 1 bond, that's 2 bonds, and that's 3 bonds. Let me erase the 1 up here. Let me make it. Oops. So that is a triple bond. Right? So they're sharing 6 electrons, it's a triple bond. So if they're sharing 4 electrons, it's a double bond. Now, I want to tell you this. Now, in this case, because they're both the same element, and you only have 2 of them, now they're contributing evenly, right? Now, they don't have to contribute evenly, okay? One could have more electronegativity than the other, right? So then you're going to, in a sense, have your uneven sharing, right? So in this case, these guys are contributing evenly, okay? So let's see if I have CO. So, and this is called carbon monoxide. Okay, how many valence electrons does carbon have?
4.
And then oxygen has how many?
6.
So we have a total of 10 electrons that we're working with. So let's go ahead, we'll put the 4 around the carbon, and you said 6 around the oxygen. Okay, so what can I do so that they both have 8 electrons around both of them?
Have a single bond.
Okay, let's see if we do a single bond. Oops. Okay, so is that 8 around carbon?
No.
So that's not reaching its octet. So what do I need to do?
Add another bond.
Okay. Let's see. Okay, is it reaching its octet now?
Yes.
Are you sure? Count the number of electrons around carbon.
Oh no, there's only 6.
Okay, so still not there.
You had another one?
Two, four, six, eight. 2, 4, 6, 8. 8 around both of them. That reaches our octet. How many electrons are we supposed to have altogether? Valence electrons?
10.
2, 4, 6, 8, 10. Piece of cake?
Yeah. Kinda.
Okay. Now what about this guy? Actually, let me give you a little more information before we get to that one. Okay, so we've talked about the concept of sharing electrons. So they're sharing the electrons. And I kind of told you a story about me and my sister and everything like that. And then I think that's kind of the point where we kind of tapped out. Okay, so when I was with my sister, we were talking about the Atari and everything like that, and that one gift. Now, I got it the majority of the time. My sister only got it part of the time. Okay, so that's uneven sharing, right? So if you're sharing evenly, both individuals are getting it the same amount of time. That's called nonpolar covalent bonds.
And unevenly is polar?
And uneven means polar. That's right. Nonpolar covalent. Okay, so and that is going to be even sharing. And then polar covalent. So try to get my brain to work here a little bit. Okay, so now I'm getting the Atari, let's say, out of a 12-hour day, I get it, let's say, 10 hours. And my sister gets it for 2 hours. Is that even sharing or is that uneven sharing? Would you say it's polar or non-polar?
Polar.
It would be polar.
Okay. Okay. Do you guys get that? You get the gist of it?
Yes.
Yeah.
Yeah.
So this is basically showing you, so when you have polar solutions, right, they're not able to conduct electricity because water, even though it forms what we call the dipole, right, meaning that you have a partial positive and a partial negative, it's partial. It's not a complete charge. So it's not going to be able to carry those electrons like sodium would, sodium chloride would, because sodium is that complete positive and that complete negative. So here we have water, pure water. No electrical charge is able to carry through it. Here we have table sugar in water, which is sucrose. Again, that is a covalent bond, right? So then it's not going to be able to conduct electricity. But if we put salt in it, we're able to conduct electricity, salt and water, okay? Because they form those complete charges, okay? So you need a complete charge. Even though water has that partial, it's not strong enough to conduct electricity. You guys get that? So,
Yes.
do you guys drink your tap water in Salinas?
No.
No.
Nope.
No.
So, do you guys have a lot of minerals? Have you ever like boiled your water till there's no more water? I do this all the time. My
Yeah.
kitchen is always smoking because of it.
Isn't that
So-
dangerous?
Yeah, it is. I keep trying to burn down the house. It just hasn't happened yet. Get real close. I talked to you about the sugar. You think I'm kidding. I get distracted. I'll be teaching, or I'll be, okay, I'm going to make a quick ramen or something like that. And I'll boil my water and forget about it. So anyway, now when you boil down, is there that nice white film at the bottom?
Yeah, nitrates.
So yeah, some of it is going to be nitrates, and then other parts of it is going to actually be your ions. It's going to be your magnesium. It's going to be lead. It's going to be, you know, hopefully it's not lead, but you know, if you're in Flint, it would be lead, you know. So in that context, that water there, right? If your water conducts electricity, you have way too many minerals in it, right? So that means that you have those ions that are floating around in it, right? And of course, we need a little bit, right? But we don't need as much, and that's in some of the waters that we have. Okay, so really what's happening in terms of covalent bonding is that you have what we call the electron cloud overlapping. Okay, so you're going over each other. So let me show you what that means. So here, this represents that hydrogen. This is that other hydrogen. When it comes together, they're going to be this electron cloud, meaning that the electrons are orbiting around both hydrogens. Now, if it's even sharing, right, that means that they're orbiting evenly around both hydrogens. If it's uneven sharing, or if it's polar, that means it's orbiting more around one than the other, spending more time around one than the other, okay? So we've already talked about Lewis dot structures. You have a good idea on that. Now you can have molecules that are, or compounds that are more than just, let's say, 2 atoms. So let's say we have H2O. How many atoms is that?
3.
3.
3, okay? Now, here's things that you want to always remember. Hydrogen can never, ever, ever be in the middle. Now, what did I just say, Vivian? You can type it up in the window, or you can tell me verbally. Are you there, Vivian? Diana, are you there?
Yes.
Okay, Diana, what did I just say?
Hydrogen could never be in the middle.
Okay, so hydrogen can never, ever be in the middle. Okay, so we know that, right? We got that tattooed on our arm. So if I ever see anybody putting hydrogen in the middle, I'm coming to your house and pounding on your door, and your family are going to say, there's this black man says he's your teacher. I'm coming for you if you put hydrogen in the middle, okay? So because we can never put hydrogen in the middle. Okay, we're clear?
Yes.
So who
Yeah.
will never be in the middle again?
Hydrogen.
Hydrogen.
Will never be in the middle. So hydrogen will never be in the middle because hydrogen only needs to have one more electron to be like a noble gas. So that means it can only form one bond, okay? So in this case of H2O, who's going to be in the middle? Who?
Oxygen.
Oxygen. So oxygen is going to be in the middle, okay? How many valence electrons does oxygen have? It has 6. Okay, how many valence electrons does hydrogen have?
1.
So one bond, one bond. So is everybody happy?
Yes.
Yep.
Is oxygen's octet filled, meaning it has 8 around it?
Yes.
Okay, good to go, pretty simple.
Yeah.
Okay. So when we get to things like carbon and oxygen. Now, the way that we determine who goes in the middle is going to be based upon what we call the electronegativity. So a quick way of determining electronegativity, if they are in the same period, the one who's closest to the noble gas is going to typically be more electronegative. Okay? Now, if you don't have that, and we have another table called the electronegativity table, our electronegativity table, you guys see it?
Yes.
Yes.
The one who has the biggest value on your electronegativity table is going to be the one who's the most electronegative. Now, looking on this table, who is the most electronegative on the table as a whole?
Chlorine.
Fluorine. Fluorine is a total asshole. He is the biggest bully you will ever meet. He is like the king. He has to get his way. So he's going to always want to make sure that his octet is filled before anybody else's, right? He's going to have the biggest pull. So he will never, ever be in the middle, okay? So how many of you guys have siblings?
Yeah.
Yeah,
Yes.
Okay, so are you the oldest or the youngest?
I'm the oldest.
Middle.
Okay, so how did you guys decide who sat in the middle when you guys have to sit in the backseat of the car?
It was for me, it was just like in order. So like youngest sits on the left side, middle kid middle, and then in the end.
That's really weird. You know that, right?
I don't know.
So
was the
in my
youngest, so I was
family,
always
the
stuck
way
in
it
the
worked
middle.
was, so when we were younger, it was the youngest, right? We've
Yep.
always pushed my little sister, my baby sister in the middle, right? So as we got older, it's a power struggle. Who's ever the strongest would get pushed in the middle, right? No, you're getting in the middle. No, you're getting in the middle. And you push them in the middle and they're in the middle, right? So that's the same thing here. So if you have a strong electronegativity, you're not going to be in the middle. You're going to push the guy who's the weakest in the middle. So the one who has the weakest electronegativity always gets pushed in the middle. Kind of like the way my house worked, right? As I got older, my sisters got really strong. They were pushing me out windows. So then I got pushed in the middle, you know? So, but don't tell I'd admit that to anybody. So. Okay, so in this case, looking at the electronegativity, who's going to be put in the middle, carbon or oxygen?
Carbon.
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 Okay. So we have carbon in the middle. How many valence electrons does carbon have?
4.
And then each of the oxygens have?
6 each.
Okay. So what do I need to do to sit there and make these guys so they have 8 electrons around them and they meet their octet obligation?
Make a double bond.
Just one double bond or a couple double bonds?
2.
I heard 2 double bonds.
2 on each side of carbon.
Okay. I'm going to start thinking you guys already done your homework and everything. You're going to have me sweating here, getting all happy, drinking to celebrate instead of drinking to be sad. Okay, so let's confirm it. So we should have a total of, what was it? 12 plus 4 is 16. So we should have a total of 16 electrons. Let's count. So that's 2, 4, 6, 8, 10, 12, 14, 16. So I got 16 electrons. So that's good. So is there 8 around this oxygen? 2, 4, 6, 8. What about this carbon?
Yes.
2, 4, 6, 8. And this oxygen?
Yeah.
2, 4, 6, 8. Piece of cake?
Yep.
Good. So now, if we looked at these two, right? We know that oxygen is more electronegative than carbon. So oxygen is going to be spending more time, the electron is going to be spending more time around the oxygen than it is going to be spinning around the carbon. So we would have a dipole moment that would be going in this direction, right? Now, the same thing is happening over here with the other oxygen. So we have a dipole going in the other direction. Now, if we added these two together, right, this will give me the dipole moment of the entire molecule. Now, the dipole moment of the entire molecule would be neutral, it would be 0, because there would be no net charge because you're pulling evenly on both sides. So you're not favoring one side or the other. So this molecule, as a molecule, would be considered to be nonpolar. But the bond, this bond between oxygen and carbon, would be considered to be polar. So we're going to be looking at bonds, and we're going to be looking at the molecule. So if we're looking at the bonds, the way that we determine if something is polar or nonpolar is by, we have these arbitrary numbers. I'm going to give you my numbers. So if the difference between the two is less than, so if X is less than 0.6, it is nonpolar. If X is greater or equal to 0.6 and less than and equal to 1.8, it's considered to be polar. And then if X is greater than 1.8, then it's considered to be ionic. Okay, so oxygen and carbon. You take the bigger number. Oxygen has an electronegativity of what?
3.4.
So 3.4, and then we subtract the electronegativity of carbon, which is
2.6.
and that's going to equal check my math. I could be wrong. So I got 0.8. So is that going to be polar or nonpolar or ionic?
Polar.
Polar.
Okay. So what about hydrogen and carbon? A bond between hydrogen and carbon. Is that going to be polar or nonpolar or ionic?
Ionic.
Okay. Do you want to do that math for me? I want you to tell me. So carbon is what? What is the value for carbon?
2.6.
And then we're going to subtract the other guy, the lower number. So which is
2.2.
okay, what does that equal?
0.4. So it's nonpolar.
Okay, so it's nonpolar, right? So it's not ionic, right?
You could also
Added them on accident.
What was that?
I added them on accident.
Okay. So what were you saying? Somebody had spoke.
Oh, I was just gonna say if we could also rule out if it was an ionic because it's two nonmetals.
That's right. Okay. Okay. Piece of cake so far?
Sort of.
That's all you always say. You never say, yeah, it's a piece of cake. I can do addition and subtraction. Yeah.
It's a piece of cake.
Okay. Okay, so we've talked about electronegativity. Now, I'm going to talk to you guys about one more thing. How we're doing on time? We're doing good so far. Got 15 minutes left. Talk about double bond, triple bond. Oh, I'm getting carried away, getting ahead of myself. Okay, so this is just basically showing us a picture of even sharing and uneven sharing. So nonpolar covalent, here we're basically showing you that both of the molecules are the same. They have the same electronegativity, so they're going to be sharing the electrons evenly. This one here, Y has a stronger electronegativity than X, so then Y is going to get that electron more, so that's why it's going to be a little bit bigger than the X, right? Because that electron is spending more time on the other side. Okay, so that's uneven sharing. And then you know what an ionic bond is. You're giving up the charge completely. It's that give and take, okay? Okay, so, and if you look on the trend on the electronegativity table, as we go down, the electronegativity decreases. As we go from right to left, the electronegativity increases. Okay, so we've already talked about multiple bonds. You're familiar with that? Pretty good so far?
Yeah.
We've talked about atoms with more than one atom, more than one atom, one type of atom. So you guys kind of got that down. Okay, so oxygen and hydrogen, are they going to form a polar bond or a non-polar bond? And if it's non-polar, which way is the dipole moment going? You want me to pull up the table? Needed this for all my classes.
It was hydrogen and oxygen, right?
Yep.
Is it polar?
That is correct. So it's going to be polar. So which way is the dipole moment going? Which way is the arrow going to point to? Meaning which way? What was that?
Towards oxygen?
Towards the oxygen. So now since both of these are going towards the oxygen, right? That means that the molecule itself is going to have a polar movement. So it's going to be, in all honesty, this is the way it's going to look. So it's going to be like this. Okay, so that means that the overall dipole moment is going to be kind of additive. So everything is going to be going towards that oxygen. Okay? So it's not the same color as the bonds. Okay, now comparing that to what we had earlier with the where these guys were moving away from each other. So do you guys kind of get that in terms of the dipole moment?
I have a question.
Yep.
Can you explain again why and they're going towards the oxygen? Is it because of the electronegativity?
That's correct.
Okay.
Because they have a stronger pull. So when we did those calculations, that number was greater than that 0.6. So that means that the electron is spending more time with the oxygen.
Okay, thank you.
And you guys understand dipole meaning two poles. So that means that this guy here is going to be partially negative. This guy, that delta means, it means change, but we use it as partial. It's not a complete negative. And this guy is going to be partial positive. Okay. And so these guys, in this case, since they're going in opposite directions, right, pulling away from the carbon, then they're going to balance each other out. They're going to kind of cancel each other out. Where this guy, they're both going in the same direction. That's going to be kind of additive. Okay. Is that clear?
Yes.
Okay. Okay. Okay, so there are exceptions to the octet rule. So one of the exceptions is if you add up all your number of valence electrons. So how many valence electrons does nitrogen have?
5. 5.
And then oxygen?
Yep.
And you get a odd number. 11 is an odd number, right? If you get an odd number, regardless of what you do, till you're blue in the face, you will never, ever reach your octet, right? Because it's an odd number. Okay? So, in that case, the guy who is the most electronegative is going to reach his octet first, and then the guy who's the least electronegative is going to try to get as close as it can to its octet. So it's going to try to get to that 7 mark, right? And so if you look around here, how many electrons do you have around nitrogen?
7.
How many do you have around oxygen?
8.
8.
Okay. What about this guy here?
There's 5 around nitrogen. 7 around nitrogen.
7 around nitrogen. And then around the oxygen?
8.
And this oxygen?
8.
Okay. Yeah. So do you guys see that?
Yeah.
Okay. So this, the other exception is, let me get my periodic table. Oops. Okay. So all of the guys that are in, I should say, these guys that are in period 3 and below, they can use the 3D orbital to store electrons, right? Where the ones that are in the second orbital, they can't do that. Since these guys can use the 3D orbital, they can, if they have to, if they absolutely must, they can actually have more than 8 electrons around them. So they can break the octet rule, okay? They don't have to. They prefer to having the octet rule, but they can break the octet rule because they can throw electrons in that d orbital, okay? So all of these guys are able to do that because they have access to the d orbital, where there's no 2d orbital. So these guys can't do that. These guys have to obey the octet rule. Okay? So when they have more than 8 electrons around them, it's called hypervalent, as in you're hyperactive. So here are examples, 2 examples of hypervalence. Okay? Are you with me still?
Yes.
Okay. Okay, now count how many electrons are around phosphorus.
10.
And then what about the sulfur in the middle?
12.
12. Okay, so now when we're talking about these guys that are hypervalent, we often have to pay attention to what we call formal charges. You guys have started the homework, you probably already ran into some issues with formal charges. So the way you calculate your formal charge is formal charge is going to be equal to the number of valence electrons minus the number of lone pair electrons minus the number of bonds. Okay, so let's look at phosphorus since it's the center atom. Okay, so how many valence electrons does phosphorus have?
5.
How many lone pair are around phosphorus?
5.
Are you sure? Right now, there's 5 around it?
None.
Lone pair are electrons that are not involved in bonding.
None.
None.
Or none. How many bonds do we have around phosphorus?
5.
So our formal charge is 0. Now, the best formal charge that you can get is 0. So a formal charge of 0 means that you're not using a lot of energy to maintain that state, right? It's a very low energy state. If you have a plus, let's say you have a number like +2, that is a horrible formal charge because that means you're spending a lot of energy to try to keep that +2 state. If you have a 0 state, that is the best state, okay? Now, if you have a polyatomic ion, that means that you have, say, as we did earlier, NO2 minus, it has a charge. Now, the sum of all of your formal charges altogether should add up to that ion, okay? So what is the formal charge of fluorine? So this was for phosphorus. So let's do for fluorine. For these fluorines on the around this phosphorus. So number of valence electrons?
7.
Number of lone pair electrons?
3.
Would that be 3 or 6?
It would be 6 because you want to count each of the electrons, lone
Okay.
pair electrons. So it's 6. And number of bonds?
1, 5,
No, you're talking about just a single phosphorus.
1.
Okay. So then that's going to equal 7 minus 6 minus 1? 0.
0.
Okay, so that tells me that this guy is perfect. That's the way it wants to be. Okay. So that's using formal charges. So on your homework assignment, if it says minimize formal charges, that means you want to try to get it as close to 0 as you can possibly get it. And that means that you're probably breaking the octet rule. Okay? So let's do the sulfur here.
Six.
Okay. Number of non-pair electrons.
0.
I mean,
And 6
Sorry.
bonds.
and 6 bonds.
So it equals 0.
Okay. And the fluorine.
7.
Okay. Number of lone pair electrons.
6.
6.
And then the number of bonds.
1.
Okay. So you just learned formal charges. So this is something that you guys are going to be using in general chemistry. I'm not going to hold you accountable on the exam, but you're going to need to do it for the homework. Do you understand?
Yeah.
Yeah.
Okay. So again, this guy's called hypervalency, meaning that you have more than 8 electrons around you. And then we have cases of hypovalency. So what do you think hypovalency means?
The opposite.
The opposite, meaning that you have less than 8 electrons around you. So there are 2 elements that are notorious for this. That is beryllium. Even though beryllium is a metal, beryllium doesn't think it's a metal. So it's going to try to form covalent bonds with certain nonmetals. And that's like fluorine and oxygen. It'll do that occasionally. In that case, beryllium is going to be happy with having only 4 electrons around it. And the other one is boron. Boron is happy with having 6 electrons around it. Okay? So those are going to be your 2 exceptions for hypovalency. Any questions?